I guess really quick, a few administrative announcements. We have some web work that's due tonight to make sure that you're finishing that up, 10.2. Today we're talking about the last, well, it's the first part of the last section for Math 133, 10.4. So we're going to be talking about polar arc length and areas between polar curves. Next week we have a quiz. The post-course surveys open and available and all that sort of stuff. Make sure you're doing that. And then also, right, you should start thinking about the final exam a little bit. Our final is going to be on Tuesday, April 28th, the same time that it was originally scheduled before we all went online and everything. There's going to be a slightly expanded time frame in which you can take the exam. So we're not going to be so strict and say you have to do it between 10 a.m. and noon, kind of how it was originally. We're opening that window up a little bit just in case if that time frame doesn't work out great for you. But you can see that it is more restrictive than maybe some of the previous quizzes and things like this. And so make sure you have that in your calendar correctly and that you don't miss this, right? It's really bad to miss the final exam. So yeah, make sure you have that marked. The other thing is that, right, if you have multiple, right, 3 or more exams scheduled on this day, right, the university allows you to make up one of these exams or reschedule it. So if you'd like to do this for your math exam, we need to know who you are and make sure that we program it in web work and everything all correctly. And so you need to email the course supervisor, Willie, by Monday, April 20th. So again, if this is you, make sure that you take care of this sooner rather than later. I think that's really all for my administrative announcements. Anything else you can think of, Alec?
I don't think so. That's pretty much it.
Okay. Super. Why don't we go ahead then, and we'll do a quick review of what you should have gotten from the pre-class videos before today's class. And of course, before class, I was messing around with all my notes on notability and whatnot, but now it's taking some time to load. And okay, here we are. Oh, I see there's a question here. How many extra credit points is the course survey? So yeah, these are the roundup surveys, and I guess there's the links down here, and you should have also gotten an email about this as well. The two of them together form 0.5% at minimum. So that way, I mean, if you are on the threshold, just shy of a 4.0 or just shy of a 3.5 or whatever it may be, right? These things together make at least 0.5%. So that way you round up to that next higher grade. So it's not a ton, but it's always really a shame, right? When you are so close to the border, right? Everyone wants it to round up. So this is a way that we can get this, and the department gets some great data as far as what we can improve for future semesters. Okay, so yes, why don't we talk 10.4 here. Again, we're talking about areas, and we're getting the third and final polar arc length, so the third arc length equation. So there's really 3 big things for this section, and they're all, in boxes as typical. So the first one is, how do you calculate out area enclosed in a polar equation or a polar curve? And so you get this first one right here, and we kind of expand on this on Calc 3, by the way, that you can come up with this formula, why this is true, very nice, but you have to use double integrals. But here, we'll just give you the formula. Notice I don't give you the proof for it. There is a little bit in the textbook, if you'd like to see a proof for this, about areas of sectors and things like this that can give you this formula. Okay, so this is kind of the base. How do you calculate out the area inside of some polar region? And we apply this a few times to a few examples. So that's the first thing to make sure that you have written down. The next thing, and so this goes a little bit into some of these intersecting functions and how you, find the R and theta values, and we'll really get into that in Monday's class. We're going to be expanding on. Notice that today's class I have it's called like arc length and nice-ish areas, and then Monday's class is less nice areas. And that's going to be going into this formula right here. Remember, maybe at the very end of Math 132, Calculus 1, And even we reviewed this at the very beginning here of Calculus 2, right? We can figure out the area trapped between a couple of curves. So here's a great picture. If you wanted to know what the area is trapped between these two curves, well, we know how to do this in the Cartesian sense. And this helps us upgrade. If you have two polar equations, how can we find the area between those polar curves? And so in this case, very similar to for the Cartesian case, right? You basically just need to apply the same formula as before, but now you have maybe a larger function and a smaller function, and you just need to subtract these because this is essentially going to be subtracting those areas from one another. And then finally, the third big equation that we need is our arc length equation. So this right here gives us how do we come up with the arc length for polar graphs. And this is something that, again, is on the formula sheet. And whenever you're given a polar equation, you want to know what the arc length is, this is the one to apply. All right, so that's kind of the pre-class videos in a nutshell. I'll pause here for a second. Are there any questions? Maybe we'll pause and let you type in anything. Alec, do you have anything to add?
Nope. Maybe just that the web work is sort of not in this same order, so they actually have all the arc length problems. If you're wondering where they are, they're all at the end of the web work.
Yeah, that's a good point. So kind of similar to the pre-class notes, but actually in today's class notes, we're going to start with polar arc length. So that may be a good few to do after class here. Okay, well, it doesn't look like we have any questions, so why don't we go ahead and move on into our stuff for today. So yeah, like I said, polar arc length in nice-ish areas. And then in Monday's class, I've nicknamed this less nice areas. So we're going to be dealing with all of these, for the most part, have multiple curves. And that's where we really get into where do these things intersect and how do we calculate out the areas in these harder cases. So that's why we have 2 days dedicated to this. So, okay, why don't we start though? Arc length is usually not so bad. So why don't we go ahead and do a few of these. Notice that in this case, I have a rather mysterious function. It's on one hand, it's very simple, but also maybe complicated, right? Because it's just r is equal to a, and it didn't specify what a is, right? Maybe a is something like 5 or 7. Maybe it's something like -2, or maybe it's 0, right? And we want to know if you have a polar equation, just r equals some constant, a, on the interval from 0 to 2 pi, right? What is the length of this curve? And so, okay, the length of the curve, again, we need to apply our arc length formula for polar equations. These are going to be theta bound, so 0 to 2 pi. And again, we're integrating with respect to theta here. So I'm looking over here in order to come up with those theta bounds. We need to take the square root, which is the same in all of our arc length formulas, right? We always have a big square root encompassing a lot of stuff. And then we have, in this case, r squared plus the derivative of r with respect to theta squared. So r squared, well, that's just going to be r is the same thing as a. So we need to go ahead and square that. And then if we take the derivative, and again, we have to think a is some constant. We don't know exactly what it is, but it's something like 5 or 7 or -2 or anything like that. And if you take the derivative of a constant, right, this is going to be 0. So here we're going to have the integral from 0 to 2 pi. We're going to have the square root of a squared with respect to theta. Well, 0 to 2 pi, again, this could be positive, it could be negative, and so maybe I'll just leave it with the absolute values, right? Usually these things cancel out. If we know for sure that a was positive, we could just, get rid of those absolute values, but we don't know for sure. Maybe it's negative in this case. So we're going to leave our absolute values just to be safe. So when we integrate this with respect to theta, we're going to have, well, you get a theta, right? This is just some constant. Again, something like 5 or 7 or something like this. And so when we integrate, right, you get that independent variable, that x usually, in this case, theta. And now we're going to range from 0 to 2 pi. Of course, when we plug in 0 into this, we're going to get 0. When we plug in 2 pi, we're going to get 2 pi times the absolute value of a. And notice this one's simple enough that there's a nice way that we can check our work with this, right? We can sketch and we know maybe what this curve would look like, right? This is just a constant distance, right? R equals some constant distance away from the center, the origin. And so whatever that A is here, it's just, no matter what your theta value is, you're always taking that same constant distance out. So this is going to make a circle of radius A. So in this case, there's a nice geometric way to check our answers, right? Arc length is going to be the same thing as circumference when it comes to circles. So we know an equation for circumference is going to be pi times diameter, or in this case, if we wanted to put it in terms of the radius, we could do pi times 2r. And so you can see that this is exactly matching up with what we have here, right? That we have an r value of a, right? And so in the case of if it's negative, right, you get all these same points, but you get them at opposite times, I suppose. You get something like this. But still, the arc length needs to be a positive value, so that's why we have those absolute values there. Okay, so this is a good kind of intro and just kind of refresher into arc length. Here's one that's a little bit more complicated, a little bit more reasonable, I would say, for, you know, to be at a quiz or exam level strength. The first one here was probably too easy, but a good warm up. So, okay, why don't we go ahead and find the arc length for this curve. So this is r equals e to the theta. So e to the theta we know is a nice increasing function. So our radiuses are going to be increasing, getting bigger and bigger. You can see it kind of starts off relatively small, and then the radius kind of spirals outwards, keeps on getting larger and larger and larger. And we're going from, again, 0 to 2 pi. So we're going to kind of do one rotation around here. And so, okay, we're going to have the arc length is going to be equal to the integral. And because we're given it in polar terms, that's the kind of the indicator that we need to use our polar arc length. So we're going to go from 0 to 2 pi. Again, we're integrating with respect to theta here. A big old square root covering everything. And the formula for the polar case is going to be r squared plus the derivative of r squared. So r squared, well, that's e to the theta. We've got to square that. And then we need to take the derivative of r with respect to theta. So that's just going to be, again, e to the theta, right? Because the derivative of e is itself. And again, we have to square that. So let's go ahead and maybe simplify a little bit. 0 to 2 pi, we're going to have the square root. We have 2, and we're going to have e to the theta, again, being squared. So we just have 2 of these things. E to the theta quantity squared. We have 1 here, 1 here. So when we add them together, we have 2 of them in total. And if you'd like to, you may be screaming at the monitor, I suppose, and say, right, when you have powers raised to more powers, that these just go ahead and multiply. So if you'd like to, you can write this as e to the 2 theta. That's certainly allowed here. But the next thing that we're about to do is apply the square root to get things to cancel. So when we apply the square root, well, the square root of 2 is just going to be 2, and the square root of something squared is just going to be itself. Again, technically you need absolute values here, but remember e is always a positive function, right? So if I was to just draw our kind of classic graph of e here, so this is maybe y is equal to e to the x, kind of the classic one here. Notice that it never takes on any negative values. You never see it down here, right, with outputs that are negative. So in this case, the absolute values aren't necessary, right? The absolute values aren't really doing anything because it's already positive. And so in this case, we can just go ahead and simplify and say that this is the same thing as e to the theta. Now we can go ahead and integrate. So the square root of 2 is just along for the ride here. And when you integrate e, you get itself. And now we can go ahead and allow this to range from 0 to 2 pi. And I made a mistake. And my question to you is, what was my mistake? Excellent. I see it here in the chat. Oh, now I see it several times. Thank you very much, guys. Yeah, I never even mentioned it, right? But we also need to evaluate out this lower bound, right, e to the 0. And quite often for a lot of functions, right, it is 0. But in this case, because it's in the exponent slot, this theta value, right, when you take e and you raise it to the 0th power, you get 1, right? Anything to the 0th power is just 1. And so you can't forget that lower bound in this case. But this is sometimes a common mistake. I see people who just say, well, plugging in 0, you get 0. And that's sometimes true, but not always true. So that's something that you do have to kind of slow down with and make sure to catch those sorts of things. Okay, any questions about this one here? I have one here, I forgot to multiply by 2. I think I have all of my multiplication correct. So I don't think I need to multiply by 2. Thank you though for the participation, I appreciate it. Okay, so this is the polar arc length stuff right here. Wait, do I have one more? I forget. Yes, I do. I have one more polar arc length, and then we're going to get into some area ones. So one more arc length. This is, again, we're kind of increasing our difficulty. So again, this one was still, we had a bit more work to do, but it was still quite reasonable. And by the time you have practice, right, you've gone through all the WebWork homeworks and things like this, you know, we're hoping that you can get to up to maybe this level right here. This is kind of maybe the upper threshold for what would be reasonable on quizzes and exams, things like that, timed assessments, right? So we want to figure out the length of the arc from theta equals 0 to theta equals 2 pi for the cardioid. And so we have a picture of this and an equation. So let's go ahead, of course, we're going to apply our arc length formula. Let's go ahead and just maybe off to the side here, I'm going to calculate out r prime, the derivative here really quick. So the derivative of 2 is 0, negative 2 is along for the ride, and the derivative of cosine is going to be negative sine. And so the negative and negative will cancel out a little bit, and we'll just have 2 sine will be our derivative. And so remember, we need that as part of our arc length formula. So length of this, and again, right, we've had 3 in a row that are 0 to 2 pi. That's the typical kind of period for a lot of these functions, and so that's probably the most common. But of course, if it said 0 to pi and it only wanted half of this, then fine, you could plug in 0 and pi into this, and that would be perfectly fine, right? So we're going the 0 to 2 pi because that's what it says for us to do, but you can see that it's not hard to extend this to other values, right? If it said 0 to pi over 2, fine, we plug in those values instead. Okay, we have a square root. We go square root here, we need r squared and we need r prime squared. So r prime, this is what we calculated out, the derivative of r with respect to theta, and r, 2 minus 2 cosine theta. You need to square that as well. And so let's go ahead and simplify this a little bit. Again, kind of maybe foiling this all out would be a good first step here. And trying to simplify as much as possible. I think we need a little bit more room, so let's expand this. Okay, so when we FOIL out this first bit, right, because this is a binomial, so really we have to have the first, the inners, the outers, the last, all that sort of stuff. Let's see, we're going to have 4 and what, minus 8 cosine of theta and plus 4 cosine squared theta. And then here we're going to have 4 sine squared theta. So again, kind of I need to square all this and kind of be careful here. No, it's sometimes tempting, especially, you know, if you're in an assessment, right, your heart's racing a little bit sort of deal, it's tempting to just go ahead and take this 2 and distribute it to each one of these things, right? And then you would just get the 4 and the 4 cosine squared, right? And so this is sometimes a common mistake, but you do have to actually do the full FOIL, right? Do the inners and the outers, and that's where that negative 8 cosine of theta comes from. All right, so with this, we can see that things simplify a little bit, right? My eyes are already drawn to the fact that we have 4 cosine squared and 4 sine squared. And I'm itching to use this cosine squared plus sine squared equals 1 sort of deal. So if I factored out that 4, this would just become 4, and cosine squared plus sine squared would become 1. So this right here is just going to be 4 altogether. That, of course, will combine nicely with this other like term, this 4 over here. And so maybe to simplify my next line here, I'm going to write 8 minus 8 cosine of theta. Let's see, I don't even need that big of a square root anymore. That's nice. All right. But still, we haven't been able to get rid of the square root altogether, right? Remember, for a lot of these things, we're trying to get rid of this square root because integrating things with square roots in general is quite difficult. And so we want to get rid of this. And there's a couple of different ways that you can go about getting rid of this. One thing that you could think about is trying to multiply by a conjugate or something like this. But on our formula sheet, it kind of gives us a nice hint on maybe what's a good way to go. On our formula sheet, it says that sine squared of some value, u, is equal to 1 minus cosine of 2u all divided by 2. And so this was the power reduction rule for sine. Quite often, right, if you wanted to integrate sine squared, you would apply this, right? Because this bit over here we can actually integrate. But we're actually seeing that there's a reason why, right, you would like to go this other way as well, because if you switch over to the other side, you get a perfect square. Right? And in this case, we really would enjoy a perfect square because we want something to cancel out with a square root. And so in this case, we're going to kind of go in the backwards direction. So let's go ahead and maybe rearrange this a little bit just to kind of make it match up with what we have here. So I'm going to multiply by 2. And I'm also going to multiply my formula by 8, right? Because I see there's a couple 8s here. So if I multiply by 8, I'd have 8 minus 8 cosine of 2u. And of course, if I do this on the right-hand side, I should probably also do it on the left-hand side. So if I multiply by 8, this is going to be 16. Oh, this is working out great, right? 16 is also a perfect square. The only thing that's not working out so great, right, is that I see that I need to have 2 times something, and I just have regular old theta over here. And that's not a huge deal, right? So we're just going to say, well, I would like 2u to be equal to theta. And that's fine. That's going to give us that then u is going to be equal to theta over 2. So when I do this exchange then, and now it's time, when I do this exchange, we're going to say the square root of, and instead of all this stuff here, right, we're going to trade it in, and we're going to write 16 sine squared, and now remember u is the same thing as theta over 2. So this is going to be theta divided by 2 d theta. So we're still keeping all of our thetas here, theta integral, and now notice that we have a nice perfect square. And so this is going to be the integral, let's see, the integral from 0 to 2 pi of 4, and the square root of sine squared, well, this is going to be the absolute value of sine d theta. All right, and we have to think about, should I leave those absolute values or can I get rid of them? And so we need to think about sine, right? As sine ranges from 0 to 2 pi. And remember, we're plugging it in, really we're taking theta divided by 2 here. So really the maximum value, even if I try to plug in 2 pi in for theta, I divide by 2, and really it's the maximum theta value that I'm plugging into sine is pi. So let's go ahead and draw a quick picture of the unit circle. And if I plug in into sine values between 0 and pi, sort of deal, because again, even though I try to plug in 2 pi, I divide it by 2, right? And so actually what I'm plugging into sine is pi. So as I plug in values from 0 to 2 pi, again, dividing by 2, so the maximum value is really pi, right? Notice that all of those values on the unit circle in this region right here, the y value is positive, right? Remember, sine is supposed to be the y value on the unit circle. So in this case, again, very similar to many, many cases, right? The absolute values really aren't doing anything, right? It's already positive. Sine is already going to be outputting positive values because remember, it's the y values of the unit circle on this region. And so here's a case, again, where the absolute values don't really do anything. So we can just get rid of them. It's just like taking the absolute value of 5, right? You just drop it, it's 5, done. All right, now we've simplified this quite significantly. And by the way, you will see there's one case, I believe, and it's a 10.4 like B sort of question where you do have to be careful. And I think there's one WebWork question where the absolute value does matter, just as kind of a heads up. So that's why I kind of take us through this entire discussion, because there will be a point at least where you should always be thinking about this and just kind of verify. Because this is sometimes where there can be a bit of a road bump or a hiccup in these problems. Okay, but with that, let's go ahead and integrate. So when I integrate sine, it's going to become negative cosine. And I'm worried about this theta over 2, right? If I took the derivative of this to see if I got back to where I started, notice I have to multiply by 1/2, right? And so I'd like to have an extra 2 here to cancel out when that 1/2 comes about from the chain rule. So double check now, if I take the derivative, I should get back to where I started. By the way, if you'd like to do this more formally with u substitution, that's certainly fine as well. You just do u is equal to theta divided by 2. And then when you take the derivative and move things around, right, you're going to get 2 du is equal to d theta, and that's where that extra 2 comes from. So this is another way to do essentially the same work. We're going to be evaluating from 0 to 2 pi. And so let's go ahead. We've got all of our constants here. We have -8 altogether, and then we're going to plug in 2 pi in for cosine. So when I plug in 2 pi, well, let's see, I have to divide that by 2, so it's really cosine of pi. So this is going to be -1. And then I'm going to subtract away, and I have to plug in 0. Well, 0 divided by 2 is still 0. So cosine of 0 is going to be 1. So I need to subtract away 1. And so let's see, we have -8 times -2, so that's going to be +16, which is great because I was a bit worried, right, with that negative and all this sort of stuff. Remember that arc length should always be a positive value, right? We're talking about how long is a curve. And so you should always get a positive value. If you ended up getting a negative value, this is a good indicator that something's gone wrong and you need to go back and check your work. And maybe that's a case where kind of those absolute values mattered, right? But like I said, in this case, they didn't. And we got a nice positive value, and this is indeed the correct answer. All right, so as promised, this is kind of, on this upper end of the spectrum. I guess maybe before we move on, really, there should be at least one question. So someone find a question for me. What's still unclear about this problem that I can, that maybe we can help with before we move on? Or Alec, do you have anything that you would like to add?
I guess the only thing I'd add is just, don't forget too, you have that graph right there, and you can kind of ask yourself, does 16 seem reasonable? You know, I mean, you can see that first little curvy part in the first quadrant. You're going from 0 to 2, you're curving, that's definitely more than 2, right? And that bottom part there is definitely, that curvy part is definitely going to be more than 2. And then that other part going over there is quite a bit more than 4. And so you can just sort of eyeball it and say, I'm pretty sure that, this thing is going to be easily more than 12. And, does 16 then seem pretty reasonable? I think it does. So it's always kind of a good idea to ask yourself when you're all done, does it seem reasonable? Yeah, even obviously it has to be more than 14, right? So
yeah, so that's a great point. Anytime you have a picture, if there's any way to check your work to see it, again, does this seem reasonable or not, is a great thing to do. All right, well, we gave a decent amount of time. We'll come back if there are any questions on this. I'm happy to answer them. Again, this is kind of the most complicated one that's, I would say, is semi-reasonable, at least for timed assignments, or very at least not, a learning set. Okay, and now we'd like to transition. I have a couple area problems for you. So we're going to find the area of the region lying inside of the inner loop of this limosome. So if you click on this, which and I loaded it beforehand, you kind of see the picture of what this looks like, 1 minus 2 sine theta. And so let me go ahead and transition. This was my other tab here in Chrome. This most always reloads if I haven't been to it for a little while. So there we go. So this is what the curve actually looks like. And I want to figure out the area inside of the inner loop is the question that was posed to me. And so I just have kind of a quick animation to go through, just kind of see how, we transverse this curve, and there we go. Now, let's see it one more time here. So you can see kind of right now we're on this outer loop, and then we transition and we're on this inner loop, right? We have negative R values at this time. And so you can kind of see we're moving backwards in order to hit this. And that goes to about here or so. And then after this, right, we're back on this outer loop. And we continue along this outer loop until the very end. So at the beginning, we're on the outer loop, and then sometime we transition, and then at the end, we're at the outer loop, right? And we want to know kind of what is this area for this inner loop. So let's go ahead and, transition back here. And iPad seems to be just a little bit frozen. There we go. And I'm going to do my, cruddiest sketch. I guess, of this picture here. And again, we're trying to figure out what is this area of this inner loop here. And so we know an area formula, right? An area formula for things like this is going to be the integral from some theta value alpha to some theta value beta, right? Quite often for angles, we use Greek letters. So theta is kind of the variable name, and this is like a to b, essentially. And the formula goes 1/2 r squared d theta. And so from this, right, we know kind of, we can easily plug in our r into this. So we're going to have the integral from alpha to beta of 1/2 of 1 minus 2 sine theta quantity squared, and we're integrating with respect to theta. But the big question here, right, is, well, we just want the inner loop part, right? We don't care about the outer loop or anything like this. So what is the range of theta values when we're on this inner loop? And the big thing that we need to realize for this problem is that when you transition from the inner loop to the outer loop, or vice versa, from the outer loop to the inner loop, right, all of this happens by going through the origin. And right, the origin has the equation r equals 0, right? The radius is 0 at that point. And so every time that we transition either from the outer loop to the inner loop or from the inner loop to the outer loop, we go through the origin, the r equals 0 value. And so if you want to know what should be the good range, you're going to take r and you're going to set it equal to 0. I forgot a 2 here. So again, this is kind of all the conceptual stuff right here. What equation should you set up and solve in order to figure out, again, when are you on this inner loop? And so now that we know, right, setting r equal to 0 is the good way to go, we can go ahead and solve. So we can rearrange this and we can get 2 sine theta is equal to 1. We can go ahead and divide by 2. And you can see we're just asking ourselves, when does sine equal 1/2? And so this is where we have to go back to our unit circle days, right? And we know a couple places where sine is equal to 1/2. For instance, one of them is going to be at pi over 6. And another one would be around like 5 pi over 6. So something like this. So pi over 6 and 5 pi over 6 are two places, right? And kind of, even though my sketch is not great at all, you can see that maybe along pi over 6 and along 2 pi over 6, right, that we would actually, right, it doesn't touch anywhere but at the origin. So remember, for a while here, we were on this outer loop. So we were plotting in these points. And then for a while, where, you know, theta is in this region, we were on this inner loop, right? Kind of, we actually went backwards a little bit. And we could even test this, right, by taking just, you know, some sampling point, for instance, like pi over 2. So if I take theta equals pi over 2, we can see that we're actually on the inner loop at that point. So let's go ahead and plug in pi over 2 to this. We get r is equal to 1 minus 2, and sine of pi over 2 is going to be 1. And so we get -1. So when I'm looking up in the pi over 2 direction, straight up, I need to go backwards 1. So this is the time where we're on this inner loop. So we start off being on the inner loop at pi over 6, and we exit at 5 pi over 6, and then after that, we're on the outer loop for the rest of our time. So let's go ahead and verify one last time, since we have this nice graphic that I spent too much time on, this is correct. So let's go back to theta equals 0. Again, for a while, we stay on this outer loop, and then right about here, we're now going backwards, and we're on this inner loop, and then we continue, we hit 5 pi over 6, and now we've transitioned back to this outer loop. Kind of, again, I'm just following kind of this point right here, and we finish up being on this outer loop. So all of this work right here, all of this thought process goes into, we need to plug in pi over 6 and 5 pi over 6 in order to figure out this area of this inner loop, because again, this is the piece that we're interested in. We have this 1/2, which, by the way, I know a lot of students, they like to kind of take constants like this out of the integral, so you're certainly allowed to do that. Take out this constant. And now we need to go ahead and FOIL out. Again, it would be a mistake to just kind of square each piece. We need to do the full foiling, the first, the inners, the outers, the last, all that sort of stuff. And so we're going to get 1, we're going to have -4 sine of theta, and we're going to have plus, let's see, 4 sine squared theta. And so, okay, this is what we need to integrate and plug in our pi over 6 to 5 pi over 6. So it looks like there's 3 pieces. 2 of them I'm not concerned about at all, right? I know how to integrate one. I know how to integrate sine. The only one that's a little bit hesitant here is sine squared, right? This is something that we need to go back to maybe our good old chapter 7 days and remember how to integrate sine squared. And the answer is, again, this formula that we brought up earlier. We have a power reduction rule for sine squared. And it goes 1 minus cosine of 2u divided by 2. So something like this. This was kind of the original direction, right? We usually went in this direction here in chapter 7 when we were interested in integrating sine squared. So let's go ahead, 1/2. And we're going to simplify for one line here. I'm going to write this 1 minus 4 sine theta plus 4. And I'm going to bring out this, right? There's this 2. There's this full division by 2. So I'm going to bring this out here, right? Instead of dividing by 2, I'm multiplying by the reciprocal, 1/2. So that's a good way to view it. And then we have 1 minus cosine of 2u. And notice my thing that's inside of sine squared here is just theta. And so in this case, it's going to be 2 theta. And if you'd like to, right, 4/2 is the same thing as 2. We can certainly simplify this. And then we could even expand this, right, kind of just distribute this 2 to each piece. And this is going to be 2 minus 2 cosine of 2 theta. So this is now kind of fully simplified. I suppose if you really wanted to, right, you could combine this 1 out here with this 2 and make that 3. But I've done enough steps in this first one, this line here. So let's go ahead and start a new line. And this is going to be where we actually evaluate out the antiderivative. So when I integrate 1, I'm going to have theta. When I integrate negative sine, I'm going to have positive cosine. When I integrate 2, I'm going to have 2 theta. Actually, this is probably a good enough time as any. Let's go ahead and combine theta and 2 theta to make 3 theta. Okay. There, now we've simplified down. And then we need to go ahead and integrate 2 cosine of 2 theta. Now I know there's going to be a sine of 2 theta. I know that this 2 is along for the ride. But right, if I took the derivative of this, I wouldn't get exactly back to where I started, right? Because of the chain rule, I'd have to do 2 cosine of 2 theta. When I take the derivative of sine, leave the inside alone, then multiply by the derivative of the inside. So I'd have an extra 2 that appears. And so that's why we need this 1/2 to cancel out with that extra 2 that appears. Again, formally, you can do this with a u substitution if you don't like this sort of guessing and checking. So the 2 and the 1/2 can certainly cancel out. And again, we need to evaluate from pi over 6 to 5 pi over 6 in order to get the area of this inner loop here. So let's go ahead. We have 1/2. We have 4, and cosine of 5 pi over 6. This is going to be negative root 3 over 2. And then we need to subtract away the cosine of pi over 6. So I'm just going to be applying these the evaluations to each kind of piece here. So when I subtract away the cosine of pi over 6, we're going to have, again, root 3 over 2. All nice together in one piece. Here we're going to have 3 theta, and so we're going to have 5 pi over 6 minus pi over 6. So again, just kind of evaluating out each piece here. Certainly allowed to do that, because you're allowed to add and subtract in any order. And then for sine, we're going to have minus sine of, oops, and let's go ahead and kind of, again, use some parentheses here. So 5 pi over 3 once we multiply it by 2. So let's go ahead and get a unit circle here. Here's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. So this is going to be negative root 3 over 2, right? That's the y value there. And then when I go ahead and I subtract away sine of pi over 3, right? Because again, I'm multiplying it by 2 here. So pi over 6 becomes pi over 3. We're up here at this point. So 1 pi over 3. So sine of this is going to be positive root 3 over 2. And again, we need to multiply all of this by 1/2. So, okay, let's see. We can simplify maybe one more line or so. I don't want to spend too much time on the algebra because we still have one more problem to do. But let's go ahead and simplify this down. Let's see, we're going to have 4 here, and let's see, negative root 3 over 2 minus an additional root 3 over 2. This is just going to be negative root 3. And then here, kind of, you can imagine these 3's canceling a little bit with the 6's on the bottom once we distribute this, and we're just going to have 2's. And so 5 pi over 2 minus a pi over 2, that's going to be 4 pi over 2, or that's going to be 2 pi altogether. And then here we're going to have minus a negative, so it's going to be plus a root 3, because right, we have 2 of these halves that are being subtracted from each other, so that would be negative root 3, but then this extra negative sign makes it positive root 3. So, okay, last line here. Let's see, let's distribute, let's see, I have some common pieces here. So I have what, negative 4 root 3 and plus an extra root 3, so this is going to be negative 3 root 3's. And let's multiply by this 1/2, so we get something like this. And then we have plus 1/2 times the 2 pi is going to be the pi. Oh, that was a lot of simplifying there at the very end. Any questions? Tempted for this one too. So negative 3 times the square root of 3 divided by 2 plus pi. So this ends up being 0.54, just at, that here. So this ends up being approximately 0.54, just kind of FYI. So the reason I wanted to do that, because maybe it's unclear that this is, first of all, positive, right? Area should be positive. This isn't net area or anything like this. And if you wanted to kind of go back to our picture here and see if this is kind of a reasonable area for this thing here. Anything you'd like to add, Alec?
No, I think you covered it pretty well.
So of course, we wanted to shorten this up. You know, if we're concerned about time for a quiz or an exam or something like this, certainly we could get to, if you get to some point like this, right, where you set up the integral. And again, still there's a lot of good thought process that you have to go through, right? What should your lower bounds of integration be? What should your upper bounds of integration be? Right, that pi over 6 and the 5 pi over 6. So you still have to think about all this, and you have to do the setup, and then maybe we could just leave it at that. So that would be a good way to save some time. And plus, I mean, when you get out into the real world anyway, right, I mean, computers will be able to evaluate any integral that you give them, right? And so it's just a matter of what integral do you want them to evaluate, right? So I mean, kind of setting up good integrals is a really valuable skill.
Yep, also any graphing calculator will do it, and there's free apps that'll do it, and free websites that'll do it. So yeah, the calculations are left to the machines usually.
Yep. But still, yeah, setting these things up is quite the important part. And in fact, in Calculus 3, a lot of weight is given to setting up problems. Of course, yeah, because we're here in Calculus 2, right, and part of it is, you know, the techniques of integration and whatnot, and how do you actually go about, that's kind of why doing things like this, you know, integrating out sine squared still has value in our class. Just kind of FYI. Okay, well, since I don't see any questions here, why don't we go ahead and move on to our last problem. This is find the area inside of one petal of this curve here. So again, I've provided some graph for us, and we want to figure out the area inside of this. And so, of course, we could set up rather quickly a decent amount of this area equation. We know we're going to need to integrate from some angle alpha to some angle beta, and we're going to have 1/2 and r squared. And so in our case, r is 2 cosine of 2 theta. So this is what we want to set up. We can see that when we square the 2 cosine of 2 theta, well, we're going to have 4. So 4, and we're going to have cosine squared of 2 theta. And maybe that 4 and that 1/2 cancels a little bit, right? So we could go ahead and cancel it like so. And we're left to this. But still a big part of these things are what are our bounds for theta, right? And so, okay, well, it seems like it's in this first bit here, right? So maybe when we plug in theta equals 0, you can see we'd get out here at 2. When we plug in slightly bigger theta values, the radius seems to be decreasing a little bit, and eventually, right, one petal stops as soon as, well, we go through that origin there. And likewise, kind of if we were going backwards, we can see that this petal stops, again, when kind of maybe around this angle right here. So if we were just betting, maybe, I'd say this kind of looks like negative pi over 4, and this kind of looks like pi over 4, right? But maybe it's not exactly that. Maybe, you know, in this case, we have a computer-generated picture, so the picture's not, you know, all that bad. But certainly if I was doing it by hand, I'd certainly question my picture. And still, we'd like some maybe algebraic way to say that this isn't exactly pi over 4 and not just, you know, close to it. And so again, kind of the way that we do this is that notice that one petal stops and another petal starts whenever we go through that origin. So again, kind of here's another case where the origin is very important. So whenever we hit that origin, that's when we're going to be transferring from one petal to another. And by the way, just kind of if you were to graph this, you know, very similar to last time, as you go from 0 to 2 pi, it looks something like this. You go like this, and then you go down here, and then you go over here, and then over here, and then you make it back to the very beginning. So that's kind of how you transverse this curve here. Okay, so again, we're very interested in when do we go through the origin, when do we hit r equals 0? And so we can set up our r equation and set it equal to 0. We can go ahead and divide by 2 on both sides. And this is the place, right, we want to know when does cosine equal 0, right? And usually what I like to do when I'm solving a problem like this, right, when we have something more complicated inside of cosine, I like to go ahead and temporarily do a mini substitution, right? I want to solve this first for u. When does, what values of u make this? And then I'll solve for theta. So this is the way that I like to do. So I know cosine is equal to 0 whenever we have one of these odd multiples of pi over 2. So for instance, pi over 2, it works, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, but also you can go backwards, right? You can do negative pi over 2, you can do negative 3 pi over 2, and again, kind of backwards as much as you want this way. So that's what u values you would need in order to make this cosine equal to 0. And so if I wanted to solve for theta values, right, well, I should just take this, whatever my u values were, and I should divide them by 2. So the theta values that would make this true would be things like negative 3 pi over 4, or negative pi over 4, or positive pi over 4, right? And I'm just taking each one of these and I'm dividing it by 2 in order to get what theta value works. 3 pi over 4, so on and so forth. So now we can see it's odd multiples of pi over 4 rather than pi over 2. And of course, we're very interested in these ones right here because those were our guesses, right? We were thinking that those theta values, those angle measures that look like, you know, on this picture, right, looks like from negative pi over 4 to positive pi over 4. So now we're kind of a bit more confident that these are the correct answers, that this is not just kind of a coincidence or anything like this. So again, we want to set up from negative pi over 4 to pi over 4. And this is actually maybe a fine time. We'll get into this a bit more next time as well. But you'll also see this in your web work, homework, that sometimes you want to make use of symmetry. And so the web work will just say, you know, make use of symmetry in order to solve this, and may specify, for instance, that it wants the lower bound here to be 0, right? And so in that case, the way that you could do this, right, instead of figuring out the area of the full petal, right, you could figure out the area of just the half petal right here. And then notice that it's very symmetric, right? It's symmetric about y equals 0. So then you could just double it. So this is a way that, right, kind of last time it was a pain plugging in all of these weird angles and stuff, that this is a way to kind of save some of that. So we could go ahead and just say, using symmetry here, if I wanted to go from 0 to pi over 4, that'd be the area of half of that petal. And so we would want to double it in order to get the area of the full petal. And you're allowed to do this on quizzes and exams and things like this where you have to show your work. And again, web work will specify, right? It'll maybe give you that this lower bound has to be 0, and it'll say in the problem, use symmetry, sort of deal. So this is an option. Okay, so why don't we go ahead and solve this? I can take out this other 2 as well, and we can make 4. And now we're going from 0 to pi over 4. And again, we need to evaluate out cosine squared, right? How do we integrate cosine squared? And so just like there was a power reduction rule for sine squared, same thing for cosine squared. So let's go over here. And again, this is on the formula sheet. Cosine squared of u is equal to 1 plus cosine of 2u divided by 2. So notice the only change here is instead of 1 minus cosine of 2u, it's 1 plus cosine of 2u. And so let's go ahead and plug that in. So 1 plus cosine of 2u. Let's see. Well, we need to figure out here, right? In this one, 2 theta was equal to u. So 2 theta was equal to u. And now I need to plug in on my right-hand side 2 u's. So let's multiply by 2 here. So this should really, I need to double this, right? So instead of 2 theta, it needs to be 4 theta. So 1 plus cosine of 4 theta, you always just kind of double it there, and divided by 2. I switched pen color and that'll annoy me. There. Okay. So we can factor out this 1/2 kind of in the denominator here, and 4 divided by 2 is just going to be 2. So we can go ahead and simplify that. And now we're ready to integrate. So when we integrate 1 with respect to theta, we get theta. When we integrate cosine, you're going to get sine. But again, remember, technically this is a u substitution, right? If I take the derivative of this, I would not get back to where I started. And so I need to include this 1/4 to cancel out from the chain rule, right? We need to multiply by 4. And that 4 and the 1/4 would cancel out, and now we get cosine of 4 theta. We need to evaluate this from 0 to pi over 4. And okay, so we have 2, and if I go ahead and I plug in pi over 4 everywhere, so pi over 4, and sine of 4 times pi over 4, that's going to be sine of pi. Well, sine of pi is just going to be 0. Okay, times 1/4, who cares? And then when we go ahead and we subtract, well, we're going to have 2, and plugging in 0 is going to be 0, plugging in 0 into sine, we're also going to get 0. So this, the final answer is just going to be pi over 2, and then we're adding and subtracting a lot of zeros here. So this right here would be our final answer. And you can see that exchanging our lower bound for 0 here, rather than having this negative pi over 4, that made it kind of a lot nicer to evaluate as well. So sometimes using symmetry makes things a bit cleaner when you actually go to do the evaluation. Things I'm missing or things you'd like to add, Alec?
I don't think there's anything missing there. I'll just remind everybody again that we went a little out of order from the way the web work is. So we didn't really cover the first 3 problems on web work. So, you know, they're not too hard. You can watch the other videos and certainly do it if you want to read in the book. But you could also just hold off on those first 3 because we'll come back to that on Monday. This problem that we just did right here is very much like web work number 6. And those types of problems start with like web work number 4. And then all those arc length that we did at the beginning, those are actually at the very end of the web work.
Excellent. So yeah, and then next time, you see I already have it loaded in here that we'll be covering some, these less nice areas, things where we have multiple curves. And so a lot of these here, they get a little bit messy.
And those finding where, part of that is finding where those curves cross, and that's really what the first 3 web work problems are. They don't even give you graphs necessarily, they just give you 2 equations and polar equations and ask where they intersect, which is the first step in doing these types of trickier problems.
Yeah, and certainly I've seen a fair amount of quiz and exam questions as well where graphs are not given to you necessarily. I mean, we are still in learning mode, and I think a great part of, or what I found very useful as a student for learning is being able to make these connections, kind of what it looks like visually versus what the algebra looks like. And so the only kind of bad thing that can happen is that we don't want it to become a crutch by any means, right? So I mean, right now we're still in the learning mode. We're still trying to connect why we set r equal to 0. What do the solutions look like visually, but eventually, right, you may not have pictures all the time. So you can't rely necessarily that you're going to have pictures. But again, I think it's a good way to kind of learn this stuff. Okay, well, I think this is probably a good point. We'll stop the recording here.